We've seen a few cases where a number is like 0. In weekday arithmetic, adding 7 changes nothing. Monday plus 7 is still Monday. In clock arithmetic, adding 12 changes nothing. 9 o'clock plus 12 equals 9 o'clock. We can formalize this notion by introducing modular arithmetic. Let a, b, and n be integers. We say that a is congruent to b modulo n, written a equivalent to b mod n, if n divides the difference a minus b. And one quick note. The symbol we're using is generally known as an equivalent symbol. So we'll sometimes say equivalent to when we really should be saying congruent to. Well, Emerson. We also write this as this way or as this way. And if the actual modulus n is understood, we just write a equivalent to b. Intuitively, the modulus is the least positive number that is like 0. Also, since 1 is a divisor of every number, it's rather pointless to write a equivalent to b mod 1. In other words, a congruent to b mod 1. So in general, we assume that n is an integer greater than 1. For example, let's show that 371 is equivalent to 326 mod 5.
Congruent.
Congruent to, sorry. And let's also find other values where 371 is congruent to 326 mod n. So remember, definitions are the whole of mathematics. All else is commentary. Let's bring in our definition of congruence. And remember, congruence mod n relies on the divisibility of the difference. So let's find that difference. And since 5 does in fact divide 45, then 371 is equivalent to...
Congruent.
Congruent to 326 mod 5. And in fact, we could go further. 371 will be congruent to 326 mod n for any n that divides that difference. So since 3 divides 45, then 371 is congruent to 326 mod 3. And since 9 divides 45, 371 is congruent to 326 mod 9. And we can find other divisors and get other congruences. Now, in many ways, this congruence is very much like equals. It is, in fact, what's called an equivalence relation. So you might remember these from other courses. An equivalence relation is one that is reflexive, symmetric, and transitive. This leads us to an important theorem. Congruence mod n is an equivalence relation. A congruent to A. If A is congruent to B, then B is congruent to A. And if A is congruent to B and B is congruent to C, then A is congruent to C. Let's prove these. Remember, the purpose of proof is that it reviews what you should know, reveals new insights, and raises new questions. For example, let's start off with reflexivity. Again, congruence relies on the difference, so that a minus a is 0, and n divides 0 for any non-zero integer n. And since a minus a is divisible by n, then a is congruent to a mod n. Next, let's prove that congruence is a symmetric relationship. In other words, if a is congruent to b, then b is congruent to a. So note that we're trying to prove a conditional. So to prove a conditional, we can begin by assuming the antecedent, the if portion. So suppose a is congruent to b mod n. Remember, definitions are the whole of mathematics. All else is commentary. And so we know that n divides a minus b. Which also means that a minus b is k times n. Now, it helps to put up the goalpost. We want to conclude that b is congruent to a mod n. So let's go ahead and write that down. But remember, the last line is what you've actually proven. So we want this someplace down here to give us some space to go between the two lines we've written. Now, the reason the definitions are so important is they work both ways. if we end with b congruent to a mod n, we know that we must have started with n divides the difference. And so we know that the difference is something times n. And so here we have a minus b. We want to somehow get to b minus a. Well, b minus a is negative kn, and there's our multiplier of n, and that links the two sides. And so our proof reads from start to finish. Now, incidentally, note that this means that the mod n should be considered as applying to the entire expression and not just to the right-hand side. Finally, let's prove transitivity. To prove that if a is congruent to b mod n and b is congruent to c mod n, then a is congruent to c mod n, we can begin by assuming the if, the two assumptions about a congruent to b and b congruent to c. And again, definitions are the whole of mathematics, all else is commentary. This means that n divides the differences, a minus b and b minus c. In other words, a minus b is something times n, and b minus c is something times n. Again, let's set up our goalpost. We want to conclude that a is congruent to c mod n, so we know that n divides a minus c, and notice if we add our two lines, we will get a minus c. So let's add, and we can factor out an n, and now we see that a minus c is n times something, so n does divide a minus c, and so we can join our start to the finish and prove transitivity.